My name is Roger Rothkamp. I work at the NASA Johnson Space Center. I'm a robotics engineer, currently working in an emerging field called wearable robotics. People are becoming more comfortable with the man and machine becoming closer together. In the past, there may have been hesitation or the technology wasn't there, it wasn't compact enough. But now we've kind of reached a tipping point of sorts where all this technology is coming together at the right time, and we're seeing a lot of applications for it, especially in spaceflight. The lower extremity exoskeleton is a wearable robotics. It's got 4 active degrees of freedom and 6 passive degrees of freedom. The applications are in assisted mobility, human augmentation, exercise, and applications that we haven't thought of yet. There are a lot of terrestrial applications. One very important application is assisted mobility, so we can assist people with paraplegia or just weakness and things like that. A key component of this project was the opportunity to work with some people that had paraplegia. The moment we got to work with them and kind of see just the energy they had to put into what we were developing, it's just exciting. I mean, there's so many applications, and you get the opportunity to work with such great people, and you get to help people. Can't beat that. We're very proud of the glove. The technology for the glove was developed in collaboration with General Motors. And with General Motors and NASA working together, developed 44 patents. And some of those patents and that technology was put into the glove to assist assembly line workers in manufacturing plants. It's dynamic. Human spaceflight is just a great cause. And now we're being able to apply that to terrestrial applications. And that just makes it that much more exciting for me. I love it. Anything you can do to make life better on Earth.
Meet Robonaut. NASA's humanoid robot is set to help man explore space. Work on the first Robonaut began in 1997. The idea was to build a humanoid robot that could assist astronauts with tasks where another pair of hands would be helpful, or to venture forth to perform jobs either too dangerous for crew members to risk or too mundane for them to spend time on. The result was Robonaut 1, or R1, a human-like prototype of a robot that could perform maintenance tasks or be mounted on a set of wheels to explore distant destinations. Through 2006, R1 performed in numerous experiments in a variety of laboratory and field test environments, proving that the concept of a robotic assistant was valid. In 2006, the automotive company General Motors expressed interest in the robotic project and proposed to team up with NASA. A Space Act agreement was signed in 2007 to allow GM and NASA to pool resources and work together on the next generation Robonaut. Robonaut 1 was the first model and has been followed by subsequent models leading up to the current Robonaut 2. The core idea behind the Robonaut series is to have a humanoid machine working alongside astronauts. In February 2010, R2 was unveiled, a faster, more dexterous, more technologically advanced humanoid robot than had ever been seen before. The International Space Station is only the first of R2's possible missions. As R2 technology matures, similar robots could be sent deeper into space to test the system in more extreme thermal and radiation conditions. Someday, R2 could serve as communications, weather, and reconnaissance satellites which have direct benefits on Earth. Robonaut 2 was launched on February 24, 2011, and was delivered to the International Space Station. NASA's experience with R2 will help them understand its capabilities for possible deep space missions. R2's head houses not its brain, but its vision equipment. R2 has 3 degrees of freedom in its neck, allowing it to look left, right, up, or down. Each arm is approximately 2 feet 8 inches long, giving the R2 a total wingspan of 8 feet. Robonaut 2's hands have 12 degrees of freedom, 4 degrees of freedom in the thumb, 3 degrees of freedom each in the index and middle fingers, and 1 each in the ring and pinky fingers. Each finger has a grasping force of 5 pounds. Behind R2's visor are 4 visible light cameras. 2 provide stereo vision for the robot and its operators, and 2 auxiliary cameras. A 5th infrared camera is housed in the mouth area for depth perception. Each arm boasts 7 degrees of freedom and the strength to hold 20 pounds in any pose in Earth's gravity. Here on Earth and at the space station, R2's backpack holds its power conversion system, allowing it basically to be plugged in. On another planetary surface, or on the moon or an asteroid, the backpack would hold the robot's batteries. R2 thinks with its stomach, literally. With its head full of cameras, the only place with enough room for a brain is the robot's torso. R2 operators have several choices for how to control the robot. Station crew members will be able to operate R2 as well as controllers on the ground. However, one of the improvements over the previous Robonaut generation is that R2 doesn't need constant supervision. In anticipation of a future destination in which distance and time delays would make continuous management problematic, R2 was designed to be set to tasks and then carry them through autonomously with periodic status checks. Mobility options for Robonaut are currently being tested. One was a 4-wheeled base, tested during the 2011 RATS, or Research and Technology Studies mission in the Arizona desert. During the past decade, NASA gained significant expertise in building robotic technologies for space applications. NASA's experience with R2 on the space station will help them understand their capabilities for possible deep space missions. These capabilities will help NASA launch a bold new era of space exploration. The next step for robotic capabilities such as R2 would be to explore near-Earth objects, including asteroids and comets, and eventually Mars and Mars moons. The robot will serve as a scout, providing advanced maps and soil samples, and begin work on the infrastructure that astronauts would need. The crew that follows would then be much more prepared for the exploration ahead. Humans and robots exploring our solar system together will provide greater results than either could achieve alone.
Capability made the crew in the ways that I've suggested. We first went after creating a system that moved like the crew, had the same speeds, the same joint motions. If you want to create a robot that interacts with the crew with the same tools and the same workspaces and the same hardware, in the end you're going to design a system that looks very similar to a person. And so you're going to have an anthropomorphic system that looks much like a person. So we see this technology with trying to create a robot or a system that moves kinematically and at the same velocity, has some of the same strength, endurance, or actually exceeds the strength and endurance of a human. And so here we'll show you a little demonstration of showing a robot that has that kind of capability. And all this goes to telling a very intricate story, which is, in the end, like I said earlier, you want to create a robot or a robot system that works well with people. Well, along the way, you need certain building blocks. And like I said, creating a system that has similar speeds was the first part of that building block. You have a little fun with the robot, but So this kind of gives you an idea of what kind of... Actually, we took out most of the matrix sequence because management didn't like it. But we kind of pared it down, and at 2 in the morning, it's kind of interesting. But this kind of shows you what kind of workspace the robot encompasses. It's a very similar workspace that you and I have. Again, we felt that was very important. So the motions, the inherent motions, the intrinsic motion that the robot's able to produce matches that of the human quite nice. It actually has a lot more range of motion than a human does. For example, I can't turn my wrist 360 degrees, but it can. I can't turn my neck all the way around. I probably could, but they'd have to replace me soon after that. But this robot can. But another key ingredient to creating this human-robotic partnership that will be successful is you need a certain amount of dexterity. And so we really went after the hand design on this robot. What separates this robot among a lot of other robots for this particular class is the amount of motion, the amount of dexterous motion, the amount of range of motion that our fingers has, the ability to manipulate those objects, and the kind of grasp forces that we can create on those objects. And so that really is a key discriminator that you don't necessarily see in other robots of this similar weight class. And that weight class is very important. Like I said, we wanted to create a robot that had a similar size and shape as a human. It's a little on the larger side. The biceps are smaller than the largest recorded size that Arnold gave when he was winning Mr. Universe. And it has the wingspan that's less than Yao Ming. So it falls within human data, albeit on the larger side of human data. But so, like I said, we've built up this range of motion story. We've got this dexterity motion. So then we have to tackle what those key ingredients are to working close and safe with people. And so this manipulator is very different from a lot of other robots that you might come in contact with. It's not a positionally controlled manipulator. In industrial robotic systems like painting robots, welding robots, general assembly robots for manufacturing line pick-and-place machines, they're very highly precise positioning devices. But what comes with that is this inability to control contact dynamics or contact forces really well. And so what we have done is we've created a really soft and loose system. So this robot has intrinsic force sensing that's also a compliant member, or a member that flexes around a lot, that we measure the torques and the forces that it creates. So what that allows us to do, it allows us to act like more of what a human does. So I'm a real floppy system, but I can also be a real stiff system at the same time. And so we can vary that stiffness in this robot just the same way that a human does. And this is very important for doing real work, because when you do an activity, you at times are stiff and you at times are loose, depending on what you're doing. And so if I come out here, the palm has and you can see it kind of rebounding, like the spring motion, and so it has a certain stiffness to it, but I can vary that stiffness in 3D space. I can also vary what part of the robot manipulator I choose to be out stiff. For example, the elbow isn't nearly as stiff as the palm is. And so when I am doing assembly activities or construction activities, this is a very key feature to doing work really well. So positional robots don't do the round peg and the round hole trick well, because if they're off ever so slightly, they build up gigantic contact forces. So what this allows us to do is, using this type of technology, is to feel that peg into the hole. And actually, it's a little counterintuitive, but you actually get the task done a lot quicker, more successfully, and a lot safer. So you can, it's okay. So you can feel the rebound. Just push right on the palm here, and you can feel, pull it towards you. You can feel how hard it is to pull towards. That's good. That's good. Thank you. And then pull on the elbow here, and you can feel that it's fundamentally. Yeah, go ahead and pull it out. So you can feel that it's not nearly as stiff as the palm is.
Right.
Now we'll stiffen that up, and you can see that now it's a lot harder to pull out.
Oh, yeah.
So there you go. So that type of technology also allows us to create another important building block with humans and robots, which is safety, of course. And so I can give you this presentation, And if this was a big factory robot that had a big painting device that was going to paint a car frame on down the line, you would see a gigantic light curtain. You would see, a cage that they wouldn't let you anywhere near. That, if you were an intruder into that cage, a big steel frame would come down. You'd be put in handcuffs because you'd be worried about getting killed. And I'm going to stand out of this way because the speed of the arm still looks pretty quick, right? And these are 50-pound arms, and if I got hit with that with some significant velocity, if I was up against a hard object, it's going to hurt. It could theoretically break the bone. It could. So now, having solved that, I'm going to stand right here, continue giving the presentation, and what you're going to see is I can stop the action of the manipulator just effortlessly. And so that allows us to interact with the robot shoulder to shoulder, elbow to elbow, while we're doing our assembly tasks, and not have too much concern about the robot bumping into us. When you're working next to someone, it is commonplace to bump into that person, because we're big compliant floppy systems, and you don't worry about breaking your elbow by accidentally touching someone, right? Well, we need to keep that same sort of idea as we build robots that interact with people. And so this is that type of technology and that type of safety is absolutely imperative in moving forward to creating these systems that are viable for human-robotic partnerships. What you do with all that is you do work. And so that's another very key difference that discriminates this robot from some other robots that you might see on YouTube, doing fancy dance moves and playing trumpets and violins and conducting symphonies and whatnot. This robot was designed from the ground up to manipulate objects. And in particular, what robots haven't done well previously is manipulate objects that aren't spatially deterministic. When you have a blanket, for example, or a mylar fabric, or a cloth, or something that's covering something you'd like to get to, you first have to remove it. And that's actually a big problem on the space station right now. Is a lot of these orbital replacement units. In fact, even the robotic replaceable units are covered with a fabric first that has to be removed before that the robot can replace the item. And so it would have been better, in my opinion, to create a robot that had the capability to remove the fabric to begin with. And so we'll demonstrate that to you here. But again, blankets are bad because you just don't, it's not a rigid object. And so you don't have, it's not easily understood as to where the object is going to be in space. So there's an envelope under it. So not only is a blanket a floppy object, but so is an envelope. And another important aspect is being able to use the robot and use the sensors that are available to it. So this robot right now is performing some machine algorithms on this envelope, waiting for me to take it from it. So you have to embed a certain amount of intelligence into the robot system in order for it to be a usable product. Right? So you're going to see payloads on the single kilogram level, 1 or 2 kilos. And what we're able to do, actually, I'd like my lovely assistant to come out here with the weight. And, he's actually volunteer. Yeah. Or we could use a volunteer. Okay, so pound for pound, this robot doesn't have as much strength and capability as a human being. Muscles are very well engineered devices for how much they weigh, and it's gonna be a while until we have actuation devices that rival the strength of a human. However, one advantage that we have over humans is we have an endurance level, or robots have an endurance level that far exceeds humans. And I'll attempt to demonstrate a little bit of that right now. So we're going to do a weightlifting demo. This is 20 pounds. And we're going to show you that the robot's able to manipulate it around with relative ease but we're also going to put it in configurations that everyone knows, and while you're watching this, are going to be rather painful. And so that'll kind of highlight the idea that I'm trying to get across. So that hand in particular is a hand that can manipulate a blanket. It can handle an envelope, and it can also hold 20-pound weight. And so this part's pretty easy, right? I mean, it's just standard. You just get in the gym, you pick up your dumbbells, you start doing some curls, right? You kind of feel it burn a little bit, but you're still feeling pretty good about yourself. And then you see, like, you know, this cute person across the way, you want to start showing off a little bit. And so you, So Adam's a pretty big guy, right? And so Adam's a pretty big guy, and he can manipulate the weight fine, but when we pause for dramatic effect, it becomes very painful for Adam to keep going. And I won't so let's keep going before we take him to the hospital with a hernia. And just to show you that, yes, we don't have actuators that can lift as much as Adam can for how much Adam weighs, but without any effort, we can exceed his endurance level. That's a very important point, is that robots tend to do things really, really well that we don't. In the end, we've got to create devices that are pleasant to be around and that are friendly for people to interact with. And so I'm going to give the robot a handshake because it did a really good job today. But actually, I'll introduce this. Again, this handshake also highlights a few of the other technologies that I was speaking about earlier. The robot's going to sense the force of me gripping the hand, and when I initiate a handshake, just kind of when you walk up to someone, you initiate a handshake, somebody starts pumping first, right? And so you kind of get this leader-follower action that kind of starts, and so. And it's a ham, but you know that technology, that intrinsic technology that allows it to kind of feel, you know, that allows it to kind of understand the forces that are being imparted on it and the forces that are imparted on the environment is the core of the system.
On board, this is Robonaut 2, and I'd like to take this opportunity to thank all the engineers that got this guy ready to fly in quite a hurry. I think just a little while ago he didn't even know he'd be on the space station, and now he's up here with us, and we're going to see what Robonaut can do. So thanks to everybody who worked so hard to get him ready. We know it was a lot of work, and we're happy to have him aboard.
And Station Huntsville, of course, the Robonaut team is cheering here. Awesome job. And are you sure this guy isn't related to Hal?
Oh, you know, since we found him already controlling... Since we already found him controlling the space station, we're sure that he is related to Hal. But we'll see. It's actually a fascinating partnership, you know, NASA and GM, in terms of the robotics involved in Robonaut, and we're really looking forward to understanding how he works and how he can work with us. It's a real good opportunity to help understand the interface between humans and robotics here in space.
And Station Houston, we copy all. Thanks for those words, Katie, but how come we never see Dima and Robonaut in the same picture?
Houston, we've been wondering exactly the same thing. We'll keep you posted.
Just checking.
I'd like to introduce you to the newest member of our crew. We're not sure if he's Expedition 26 or Expedition 27, but he's definitely on board. This is Robonaut 2, and I'd like to take this opportunity to thank all the engineers that got this guy ready to
am recording this.
Yeah, Katie, just want to confirm that you removed the motion stop from the phone.
You guys never told us there was a motion stop in there. When we threw that phone out this morning,
Oh, come on.
So, Vern, I'm making a joke because it was written 9 times in the procedure, and yes, we retrieved the motion stop.
We'll thunder on top of you.
Well, we thank you. You've got us speechless down here. And by the way, we love the video.
So you're getting live video right now, are you?
Yes, it is.
Okay, and we already recorded this for the procedure before we just did the survey since live. We can send you the link. Just to catch you up.
Yeah.
Just to catch you up, we actually did this exact procedure just earlier today. And so we've got, and we put the camera on, so there's video of all of it. We like it that we have 2 cameras, so you've got 2 camera views, about an hour long too of taking the robot out and disassembling. You can think about if you want that and when you want that. And I think we did everything for the procedure. There's going to check the steps are still undone, and then we need to hear the program. Just too close for it to focus in the phone.
We copy all, Katie. And, yeah, we'll let you know when we get ready for the downlink.
And he really did come out and just fine-tune the procedures for some of the tools for
Can you move the box?
We appreciate those words. And, yeah, he looks great. Made our day.
And just for your information, I have actually seen that at the same time, so I'm sure.
Do they want to see anything special under here? Because I don't know what they're...
Good to know.
You saw the power connectors?
Yeah, I see it, but the power connector is capped. So do they want to see anything else special?
Can you ask them?
And that's the pellets showing you the power connectors. They're capped. Is there anything special you want to see right here?
Anything else?
Stand by one. ROBONAUT team says nothing special. They like the view and what they say is good. So nothing else required on that. They saw all the power switch and everything. Thanks.
Copy. And we really do want to thank you for the instructions and the phone. That was very, very helpful. And then, of course, Schleifers was involved to a large extent as well. And, you know, those things might seem small, but they are big in dramatic procedures, and some of their notices was very, very helpful. So thanks to the team for that. And I know it really must have been so much work to get it ready. It's Q3, and I know launch was delayed because that doesn't help that you guys were all ready for launch, and it was ready for launch. So I know that was a tremendous amount of work. And times like this today, when he's breaking up, get all systems on.
We concur, Katie. Of course, for a while you had us thinking he missed the launch.
It's enough.